I think this part we already explained it once, but then let's just redo this once again. Okay. So what happens generally is that you are considering a function. We are dealing with the chapter of transformation. So whenever we have a function, this function will be dependent on certain parameters, and the parameters that we are going to consider here is nothing but the generalized coordinate, the generalized momentum, and time. Okay. So when we actually take the differential form of this, we can just write it down as df dt of qj, pj, and t. Okay. And if we really differentiate it with respect to time, by which we are not, yeah, any questions? Okay. So when we actually differentiate it with respect to time, we do have the three components there. Okay. Del f del qj, qj dot, del f del pj, pj dot, and del f del t, right? So this is something which we have already seen. And then I told you that we can actually use the Hamiltonian for the replacement. So qj dot can be written as del h del pj, and pj dot can be written as minus del h del qj, right? So once we do that replacement, we have this bracketed term to be having two
Not visible,
different.
sir.
The slides are not visible. Okay, just wait. Let me check. I think I've already shared. Anyone else can't see the slides? I'll continue. So I said that whenever we are talking about Poisson bracket, we need two functions. And if the example we can see within the bracketed term, it is a function of f and it is a function of h. So there are two functions f and h. And this bracketed term will comprise the Poisson's bracket of f and h. So it's not that always we are going to have f and h. It can be any kind of function. And that's just an example that we're considering. Okay. So if we just consider that, we basically say xy as the general function. And then if we want to write down the Poisson bracket, this is the most important part if we want to do any numerical. Okay. So the first function will be differentiated with the generalized coordinate qj, and the second function will be differentiated with respect to the generalized momentum pj. And then you subtract and you just reverse the variables with which you are going to differentiate, right? So this is something which we have seen, and we have also seen some properties. Not going to repeat that. Okay. The most important part is whenever you are going to prove whether transformation is canonical or not, is this is the first part. And I told you in the last class that this is quite obvious, because whenever you are having x and x, not x and y, we can have x and x. Okay. So we can just replace this y by x, this y by x. So this term and this term are the same. So we are subtracting the same term one from the other. So that becomes 0. So the first condition is automatically fulfilled. But that doesn't mean that it will be a Poisson's bracket. Okay. There has to be an additional condition. The additional condition is that if I is equal to j, that means you are considering the generalized coordinate and the generalized momentum of the same point, okay, of the same particle. You are going to basically get the Poisson bracket as 1. If you get the Poisson bracket as 1, then we can say that the transformation is canonical in nature. So this is something which we are going to see now. Okay, we are going to take some example, and this thing is going to be more clear. So, there is an invariance of Poisson's bracket with the canonical transformation. Okay. So more or less the end result will remain the same. Okay. So invariant and covariance also we have seen. Okay. Let's just jump to an example here. And this is an example which we have seen even in the exact differential method. But what you will observe in Poisson's bracket is that this is kind of a bit easy compared to that what you did with exact differential. In exact differential, the second function f, okay, both the functions should be same, and the second one you have to kind of guess and then check whether it's correct or not. Okay, but then this is more straightforward. But if in exam it is asked, it's important that you answer it according to the question. So if I just write down is canonical using Poisson's bracket, you can use the method that we are showing now. But if I just say show that the transformation is canonical, you can use any of them. You can use an exact differential method. You can use a Poisson's bracket method. But if I ask you is canonical using exact differential method, you have to use the previous method that we have discussed. So let's just try for the canonical method understanding of the canonical system, right? So what happens is you have got two here. It is q and it's p. So what we can do is we can actually take four differential equations here. So the first one, let's say it can be written in this form. See, 10q can be written as q by p. So if you look into here, into uh, this is a mix, okay? This is q and this side is capital P. This is small p, this side it is capital Q and capital P, okay? So what we can do is we can write down the equation in terms of capital Q and capital P on one side and small q and small p on the other side. So the important part is you have to separate the variables on both sides. One side it should be only the, let's say, the new set of coordinate system, let's say capital Q and capital P, and on the other side it might be the old set of coordinate system, small q and small p. So this can be done just by using a bit of geometry here. So you can actually divide, okay, one by the other. So you can always do this. You can divide this by this. So you'll get q by p, and this will be nothing but 10q. So you got one expression for capital Q, and then for capital P, you can just add and square both sides, right? So when you add and square both sides, you are going to get this particular equation. So it depends on how you write down the equation, but then that is the first step that we need to follow, okay? And let's check the Poisson's bracket condition now. So as I said, the first condition, QQPP is equal to 0. It is already satisfied by default. It will be satisfied, okay? But then this is not the sufficient condition, okay? You remember some terms like necessary and sufficient condition. But that's not the only condition that needs to be satisfied. We need to check this condition. So whenever you are dealing with Poisson's bracket, you are more or less going to talk about this particular condition and see whether this is getting satisfied or not. So you see, I already have an equation in terms of capital P and capital Q. Capital Q is tan inverse of Q by P. We'll use that. Okay? So let's write down the first part here. So we have to show, okay, this is our aim. We have to show that QP is equal to 1. Okay. And whenever we have a Poisson's bracket, see this, please note this is within square bracket, okay? So if there is a curly bracket or there is a first bracket or if there are just a modular sign, that does not represent Poisson bracket, okay? So the representation is important. So del Q del P, so you will always differentiate it with respect to the old set of coordinates. So the old set of generalized coordinate has got small q and small p. So it will be capital Q, small q, capital P, del P, minus capital Q del small p del capital P del small q. So that's the way you are actually writing it. And now everything is more or less mechanical, very much trivial. You can just follow the steps here. So what you see here is the first thing I have to find out is del Q del P. Okay. So let's just find out del Q del Q. Sorry, not del P, del Q del Q. So it will be del Q of tan inverse of Q by P. Okay. So we have already written that capital Q in terms of small q and small p, and we can just differentiate it. Okay, then we definitely need to remember some certain results. So if you have forgotten your trigonometry, probably you can just revise it a bit. Okay, so we can actually always do the uh, basically you can just replace it with another variable and then you can differentiate, right? You can always take this as x, so it will be del x of del x del q, right? So we can always take that. So del x of tan inverse of x del q, and x is equal to q divided by p. Okay? And you know del theta of tan inverse of theta is 1 divided by 1 plus theta square, right? So if you remember that, you can just simply put this result. This result is here, okay? And then this is this del q of q by p, okay? So that's just 1 by p. So you can just put the values here, and then what you have is 1 plus x square, okay? And just cross multiply that and try to get a form of the equation. Del q by del q is equal to 1 by p, right? And then what you can do is this, just replace this x by q by p square. Obviously we cannot keep x there, that was not the original form. So it is q by p whole square and del q, okay? You can just do this sum and then you can just simplify this and find out what is del q by del q. Done. Let's do del p by del p, and del of capital P we have seen it is half of q square per p square, relatively a simpler expression compared to the first one. So you can just write down the relation as just p. You can just differentiate and see that this is just p. The next term, del q del small p now. Okay, so this is this term. So again, you can do this. You can do this x and this. So you know when you take del p of q divided by p, it will be minus of q divided by p square. In this particular case, q is basically considered as constant, right? Then just take that out, and del p of 1 by p is minus of 1 by p square, right? And then this will remain the same. And then you can just replace x by q by p. Just do the simplification, and you basically get this result. Okay. So you have to have all the terms in the simplest form so that you basically get back your final answer in a much easier way. Okay. So del p del q would be nothing but small q. Okay. So once we have this, we can just replace. So let's just do the replacement here. So if you remember, this was minus of q by p square plus q square. So that means this minus minus will become plus here. Okay. So we have one term here and one term here, and we can add them up. So you see, you can consider 1 divided by p square plus q square common. So this term is common, right? This is common. You can just take out common, and then on top it is p square plus q square. So you can just do this, and then finally you get the result as 1. So then we can easily say that this transformation is canonical in nature. So this is how you actually prove whether a transformation is canonical or not using Poisson's bracket. What is the main formula that we use? We simply use the relation of the two set of functions that we have, and we differentiate it with respect to q and p. Just reverse them, subtract one from the other. To get one, it is canonical. Please remember, sometimes even in entrance exam I've seen, it's not that all the expressions that are given will be canonical. Okay, sometimes you'll see that it doesn't turn out to be one. So if it does not turn out to be one, that's definitely not canonical. So you have to be very careful when you do the calculation. Okay, so in exam also, I won't give you a very complicated problem, but then it may not be the case that I will give you the same problem that I'm discussing now. Okay, so you have to understand the essence. I have to understand that what exactly are we doing, and if you know the steps, you can easily do it in your exam. Okay, so that's very important. I guess all of us know that answering a problem based on the concept that we have is far more important than just remembering an answer to a problem. Okay, that's not the way that we study. So for the question, this question is kind of similar, but then I think this is simple. You can understand this very easily. The question is, you have m and n in the functions given, capital Q, capital P. You've got m and n, okay? And they will basically give you these two equation, these two transformation equation. You see, everything is written in terms of q and p and small q and small p. Okay, so the question is, they are saying that this is canonical. So it is beforehand, it is mentioned it is canonical. You have to basically find out what are the values of m and n. So you can straight away equate it with 1 and then solve it and see what are the possible values of m and n for which you are getting the right hand side to be 1. Okay, and then of course they're asking obtain the generating function. Okay? So any kind of transformation will have a generating function, okay, from which you are actually can obtain the transformation equation. Okay? So we are going to try to understand this now. Okay? So this is our next problem. So it's canonical, already mentioned. So that's why it's straight away write it down as qp is equal to 1, or del q del q del p minus del q del p del q is equal to 1. So I will take this as the base equation, and then I'm going to solve it. Okay. So let's just do it, okay? Because see, it's very straightforward. You are already given it in terms of capital Q and capital P. So once it's given in that way, you can actually write down what is del Q del small q. So that will be del Q of Q to the power m cos of n p, and then this is very much simple differentiation, right? So you're just differentiating with respect to small q. So this can be taken out as constant, and this would be mq to the power m minus 1. Similarly, we can do it del p del p. So this here, this will be a constant. So this can be kept out. Okay. And the only part that we are going to differentiate is this. So you can just take this to be cos of np. You know, ddx of sin x is cos x. And differentiate np, and you just get n, right? So that's the term that we have. And then we can just do del q del small p. Okay. And then in a similar way, we can just put it, and I think this is very simple. Don't need to explain much. Please remember the minus signs and all. Okay. Whenever you are differentiating cos term, it's always minus of sign. And then del p del q we have, and then that is nothing but mq to the power m minus 1 into sine of np, right? So once we have all the forms of del q del q del p and so on, okay, we can just replace it in that equation 1. and we will just differentiate it and just put it there. Okay? So please remember, you have to practice it once so that you are confident about it. Okay? So I have done it on my own. So you also need to do it on your own. You can just have the question and try to practice it once. Okay. So when you put all the values and you can just look into the equation. In the first term, it comes out that this is cos np, this is cos np. So you'll always get a cos square np. And then you see this is q and this is q. So you can just take up the powers and add them. So it is 2m minus 1. And then there is an m and then there is an n. Oh, sorry. N is here. Yeah. So this is an n, right? So you have the first term of the equation. And for the second part, you can again see that this is n, this is, where is an m? M is there. So we have got mn. And then q to the power m, q to the power m minus 1. So it will be 2m minus 1. Okay. And then we have got sine square p is equal to 1. So I think you can easily guess now what is happening. You can always take this mq to m minus 1 q to the power 2m minus 1 as common. And then you have got this simplified expression of mn q to the power 2m minus 1 is equal to 1. So, when you arrive into such simple results and you are on the verge of getting an answer, you actually have that different sense of satisfaction, right? I think all of us know this, okay? Usually in math, it usually happens. So you see, what happens is that this side, there is a way, different ways of solving this. But then this side, you can always write it down in this way, right? It is q e to the power 0. So that is 1. So you can just equate this and this side. Okay, that's obvious as per geometry. So 2m minus 1 must be equal to 0. So you can just put m is equal to half. So you can just find out what is m. M is nothing but half, right? And then you can just put that value of half. And then if you put m is equal to half, this becomes 0. So you can just find out what is m. So n is 2. So this way, you can actually write down what is your final expression. So in the final expression, you have to just replace the value of m with half. Okay, okay, m with half, okay, and then n with 2. So this is your n, right? So that's important. So this is the expression that we have. The next term, the next target is to find out what is the generating function. Okay. So generating function, we have seen 4 types of generating function: f1, f2, f3, and f4. And this particular form, we can take up. It is in the terms of if we combine both of them. Okay. If we just combine both of them, so we can square and add on both sides. Okay. Or we can actually just divide it throughout. Okay, that is also possible. So you see that this basically can be written in terms of small k and capital Q. Okay, so please try to figure it out, because I think generating function we have already discussed. Whenever we are talking about generating function, it's important that we need to write down it in terms of a function. Okay, so if we can write it down in terms of small p and capital Q, we can actually get the generating function here. So we can actually just put it here. Okay, small q is q square sec square 2p. Okay, and once we have this, okay, so you see this part. So this is something which I'll give you as a homework. Okay, let me not explain this. You try to figure it out how exactly you need to do it. Okay, once you do it, the generating function final answer that you should get is, let me just show you the final answer here, and then you can explain it to me in the next class. If you're not able to explain it, I'll explain it. So f3 is minus half q square sine of 2p.